In this lecture, now we're going to continue to the latest architecture that made a huge impact on the field. Transformers, they probably estimated that they brought about $1 trillion to the artificial intelligence community with all these companies like NVIDIA, Meta, Google, so on, and OpenAI, not to mention. And just to be sure, I'm not talking about the cartoon transformer or the electric device transformer. It's about the neural network architecture. This lecture was heavily involved by Andrej Karpathy's lecture on transformers, and a few online tutorials, including the MIT course that we will have links for all of the piece of information here. So um, let's get into it. Okay, so I'm gonna start off with the limits of convolutional neural networks. Then we'll motivate the transformer, like how the transformer has been able to overcome those limits and even add more to it. Then we'll take a close look at the anatomy of the transformer. So how does it work? Finally, we'll make the jump to vision transformers, and we'll close with some conclusions on transformers. Okay, so the first limit of the transformers was that they are really susceptible to image transformations. So if you had this original image here, and then if you rotate it, the performance of the transformer would drop of its own, by its own, right? So the architecture doesn't have a way to take into account all of these transformations directly, right? If you scale the image or you change the brightness, the performance would drop. Now, as you know, and Eugene explained it pretty well, this problem was alleviated with data augmentations. So during the time of the training of your convolutional neural network, you would apply all of these transformations, and you would also apply your ground truth data, and so the model learns the transformed images as well, right? But it's important to note that for the model's sake, a scaled image is a different image than the original image, right? But it has now learned to recognize the scaled image as well. But the model doesn't know that this is the same image transformed, right? And that's why it's important that we manually or like we automatically apply all of these transformations and train the model on it. The next problem with the convolutional neural networks was, and this problem was very applied in the real world sense of applications of these models. So if you're thinking about robots that need to, like take a video of a scene and then, move things around, or like autonomous drivings, any robot that needs to have an eye to the real world, they would be impacted by different lighting problems, right? And this problem is shown by that, your light source could be at different locations. And this is not a trivial source of transformation that you can apply to an image from the natural world. What the people do is that they would, create video games, and in these video games, they would put the light source in different locations to generate synthetic data and train the convolutional neural networks on this. So obviously, it takes a lot of effort to create those digital twins of the real world and start manipulating in this video game environments. But people have done it and done quite well with it. Now, there's this convolutional neural networks also have the problem of partial obstruction. So if I were to label this image, should I label this image as a tree or should I label this image as a car, right? Now, if I do label it as a car, well, if a car is obstructed by a tree, then it doesn't really look like a car to a convolutional neural network. One thing that people can do with segmentation is that they can label every pixel in the image that belongs to a car, and they can label every pixel that belongs to a tree. But then, how well would it translate down the line? It's not obvious, and it's not a mathematically robust system to deal with this issue. And so this partial obstruction problem remains and has been a problem that has stopped like autonomous vehicles adoption to the real world. Yeah. Then there's two other problems with the convolutional neural networks, and it's a lack of broader context. So if you look at this image here, is this a teapot or is this a toilet? Like, I mean, it's both and it's neither at the same time. Like, it's a piece of artwork that is going on, and it's very like unclear what the artist like it's very unclear to the model to know what this is without them knowing that this is like an art statement. Let me see if I can turn on my pointer. Yeah. Okay, so we humans understand that this is a work of art, but not necessarily. It's very difficult to convey that to a convolutional neural network. Another limit of the convolutional neural networks is that they don't have a positional understanding of the features that they're extracting. So to them, an eye feature is an eye feature, and every image with an eye feature and a nose feature and a mouth feature is probably an image of a face, right? And so these two images, they look the same to convolutional neural networks because there's no understanding of the positioning that is required. But for us, it's obviously different. This is like a messed up face. It's not even a face, but this one is a face. So the problems of like lack of context and positional understanding are kind of like much more important when we are talking about processing text data, right? So one classic task in labeling text data is, for example, name entity recognition to know what is the object, what is the subject, what is the verb, and so on and so forth. And the order with which the words appear in a sentence matters a lot into the functions those words serve in that sentence. So, for example, is the cat is chasing the dog or is the dog is chasing the cat? The convolutional neural networks, they wouldn't be able to tell the difference of this. And partly all of this positional information is lost because of operations like min and max pooling, such that we use to kind of like reduce the feature dimensions, like as we go deeper into the networks. And Eugene talked about it previously. Same as the lack of context. The lack of context problem is now bigger when we're dealing with text. For example, consider the sentence, I saw her duck. Are we talking about the duck animal or are we talking about the action of ducking, like, like avoiding a ball in dodgeball, right? Obviously, for the case of like the context, you could increase the vector of words that you pass into the model, right? You could increase the size of the vector. So instead of passing duck and hare one by one, you could pass hare duck. Um, and that would increase the amount of information in a single input. And this problem is represented with n-grams, right? So n-gram is a combination of words. So a 1 gram is basically a single word like data. A 2 gram is like a multiplication of two words, so like great information. 3 gram and 4 grams and so on and so forth. Please note that the like n-gram isn't necessarily just a word. For example, synthesizer, it's a complex word, but it would be made up of two n-grams. So synthetic or synthesis, and izer, like synthesizer. So that would be like a 2 gram kind of word. And so you could, increase the number of n-grams and pass all of the larger n-grams all at once, but that comes at a cost. So when people use with like small n-grams to train convolutional neural networks for text, they have a good local understanding and they're computationally cheap, but then they're like lacking the bigger context. If you increase the number of n-grams, then you have no guarantee of, global understanding. It's unclear what the model will pay attention to, and it becomes computationally expensive to handle these longer n-grams down the line because you're applying convolutions on these n-grams and their size kind of like grows. So these are the two limits of convolutional neural networks with respect to the text. Now, people have been trying to make better and better CNNs to kind of address this issue. Specifically, they propose this recurrent neural networks. And the idea of recurrent neural network is that you can take the output of like one hidden layer, and the output of the hidden layer, instead of in addition to it going forward, but the output of the hidden layer can also go backward. Oh, uh, I went backward. That's funny. Anyways, so here in a regular convolutional neural network or unit, you're always flowing towards the outcome, like towards the end, and you're always flowing to the right. But with the recurrent neural networks, you can have the output of like one hidden layer go backwards to the previous layer, right? And so this schematically in general term is represented by this architecture or like the neural or the recurrent neuron, as they would talk about it. And this is, the H here stands for the hidden layers. And so you take the output of the hidden layers and you put it back in, and you put it back in, you put it back in. And this allows the recurrent neural networks to basically have a sense of sequence of data, right? So what you can do is that you can open up, you can unfold this act of returning the output of a layer in the front to the back. You could unfold it in time. And so you have, you can take time steps now. So t minus one, t plus one, and this will again give you a sense of sequencing. But what is tricky is now to do back propagation, right? Like if I have the derivative, or if I have the gradient of the loss function and I want to update each of these weights based on that gradient, then how am I propagating this like loop like situation? Like it drops into like an infinite loop, right? So you need to do your back propagation and updating of the weights as like a timestamp component to it as well, right? So you like back propagate information through time with the recurrent neural networks. And this allows you to have positional understanding, but there's a limit, and that was the limit of the lack of context. And the problem is that, sometimes information in the recent time, so back propagating at the current time, will overwrite the features that you extracted, like 20 time steps ago, right? So these networks may forget what was the previous information that they have been gathering. And so to increase the amount of context that recurrent neural networks could have, people have developed LSTMs, so like long short-term memory. And the basic idea of LSTMs is basically to give the models, to give each neuron the ability to choose what information they want to add, choose what information they want to forget, and choose what information they would like to pass along, right? So the LSTMs have three, I guess, like gates in them, and they have the forget gates, the input gates, and the output gates. And it's a very interesting and intelligent design. And this allows the LSTMs to actually capture longer and longer context because now the model can choose what information to let go and what new information to bring in its place. And it can also choose what information it should give to the next stage and what matters there. And that's what they're learning. However, the problem with LSTMs is that they are strictly sequential. So when you're training them, you need to train them in a strictly sequential way. And this makes it very difficult or basically impossible for them to be parallelized at scale. And so they have like a high computational complexity. Like, I mean, the computational complexity of the LSTMs itself is of ON, which is not bad at all. It's really good. The longer the sequences, the complexity linearly grows. But because you cannot parallelize it and because you have to only train it in a sequential way, you can't take advantage of the modern architecture. And so the LSTMs can memorize up to about 1,000 tokens or like sequences of about 1,000 words, whatever, right? And which is nice. 1,000 words is a lot of words. But people figured out how to do better. So now we move on to motivating the transformer. So the transformers themselves, they are trained to predict the next token in a sequence. So they have this autoregressive property, and that by default gives them dynamic positional awareness so that they can understand the positional information in your input, in your tokens, which is great. The way they do it is that for the next output that they're supposed to send out, they have learned a probability distribution over the vocabulary, right? So they have like this dictionary available, and they have learned that for the next output in the sequence, there is a probability with which like some words are more probably needed than the other words that are needed. So at each like layer, at each step along the sequence, they have these like probability shifting probability distributions over the dictionary that they have access to, and they can basically pick the words that are mostly probable for the next word, right? The transformers have also this capability. They have like many layers of attention blocks into them, and this allows them to capture local and global contexts. So if you remember, LSTMs could remember up to 1,000 tokens. Transformers might very easily scale up to 10,000 tokens all at once, and they maintain good local relationships in the data. Like they understand the locale and the global context pretty well. So this is thanks to like multiple layers of attention blocks and feed forward blocks going back anyways, and the last property of the transformers that is very valuable is that they're extremely scalable and parallelizable. And so all of the tokens could be processed all at once. And this allows, these companies to train transformers over like 10,000 GPUs or even like 100,000 GPUs, like in parallel, and then combine the output of, those GPUs, those transformers, combine them all together into like one single transformer that works very well. So you're already like learning in parallel, you're dividing the work and you're conquering the job. And this allows these transformer models to be very good for foundational models because in foundational models, you need to train on, like billions and billions of like data points. And so you could only do that in parallel. Okay. Now, the final advantage or the fourth advantage of the transformer is that they're not really bound to any like data formats, right? Like they work pretty well on text. They also work pretty well on audio, infrared images, on graphs, even for like, action and states that may happen along the way, like sequences of events in an environment. They can also learn it. If you can formulate your data in a sequence format, the transformer can learn it. So they're extremely general purpose. And this paper from 2023, actually, like they proposed meta transformer. You can take a look at the paper later on, and it shows how capable these models are across a variety of data formats that they may be out there. Okay, but how, right? Like how is Transformer able to perform so well across so many different data types? Okay, so to understand that, we need to take a look at the anatomy of a transformer. So I'll have your focus to be on the left side of the screen here. Before we can talk about how the transformer processes the data, we need to talk about the pre-processing of that data. We need to like put a lot of information, put a lot of effort to make sure that the data that we are giving to the transformer is a very good data, right? So so I'll explain what good means going step by step. So the first thing that you need to do when dealing with a like a sequence of words is you need to break that sequence up into single words or like n-grams basically, right? And then you need to kind of like map these words into basically a numerical value to like a vector value that could be done. So this process is called tokenization. It converts texts to vectors of meaningful strings. A unique token is given to every subword, and this is usually done with a rule-based algorithm. So basically, it takes up a sentence, it divides it up into tiny bits, and then it will give a vector to each. Basically, it will give a unique vector to each word, right? So this is the problem of tokenization. The next step that they do is that they do embedding generation. So what we do now is that we take those tokens and we transform them into this embedding space where words that are closer to each other in meaning are closer to each other in this embedding space, right? So if I were talking about sports and I said I saw her duck, the word duck and ball would be closer to each other in this embedding space, or the vectors that correspond to the words duck and ball would be closer into the space. If I was talking about animals, then the word duck and like seed or like feeding would be closer to each other in this embedding space, right? So this is already like doing a lot of heavy lifting of words. Like this is doing a lot of the heavy lifting that allows you to put the words that are similar to each other or like contextually related to each other. You put them closer in this embedding space, and that's really nice. It's like very high dimensional. So each word is probably like represented by about 800 or like 1,000 numerical values, numerical floating points in this vector. So the vector that describes each word is about 1,000 characters in length, right? And then, so far, okay, let me just go back. So far, there's no information regarding the order of the words in a sentence, right? I could scramble this sentence right here, and I would generate the tokens, and I would generate the embeddings, and there's no sense of order that the words happened one after the other. So how can we give that sense of like order or the sequential priority of the words? This is done thanks to positional encoding. So what they do is very simple here. They will like define like a sine and a cosine function, and the sine and cosine function has like a value that is related to the index of a token in the input, right? And so like they will take the index of the token in the sequence, and they will pass it through the sine or cosine function, and then they will add it to the embedding that was generated before. So if you look at this like vector down here, it is also up here, and then to this you just like add the positional encoding. Very simple. It's like just a very simple addition operation. So now we have our input to the transformer. It's called xi, so it's our input now. It already has a sense of positional information. It already has a certain sense of like the context or like the closeness of this token to the other tokens in this embedding space. And now we can go move forward to the attention mechanism. So the attention mechanism is very key and to the point that it was the title of the paper that proposed transformers. They mentioned it's Attention is All You Need paper back in 2017. And so to explain the attention mechanism, we have to learn three concepts, basically: query, key, and value, right? So query is basically a simple vector. It's a transformation of the input that describes, that answers the following question: what aspect of other tokens are relevant to this token, xi, right? So this is query. Query says, what do other tokens want from me, right? Key is basically what I have, right? It's basically the information in xi, and this basically says what aspect of my token is related to the others, okay? And value is basically another weight, another vector, and this describes what information should I care coming from this token, right? So these three concepts is very important. Query asks what other tokens are relevant to this token. Key says what aspects of this token are relevant to the other tokens, and the value says what information from this token should I pass on or should I pay attention to, basically. As I mentioned, you have the formula for these. This is basically a linear transformation. So, the weights, these weights are linear transformations done to the token, to the xi, and these are all learnable parameters. So during our training, we kind of have to solve for these weights, right? Like the weights for the query, the weights for the key, and the weights for the value. So these are learnable parameters. Um, okay, so how do we combine this together? First, we do like a dot product between the query and the key. And then we normalize it by the dimension of the input, and then we apply the softmax function to introduce some nonlinearity or some sort of activation that Eugene covered, right? So this will give us this A vector, and from the A vector, we do another dot product between the A vector and the value vector, and this will give us the attention vector or Z, right? So very simple operations, all, like just like a bunch of dot products and some learnable parameters. And from this, we can pass this information to the feed forward block, which Eugene already talked about. So as you can imagine, um, this attention mechanism right now is being applied only on xi, right? There's no ground truth. There's no other xj or I plus one or xi plus two and so on and so forth. We are only learning the attention. We're only applying the attention mechanism on the token itself, on xi, right? But the reality of the situation is that we have multiple words in a sentence. So we have multiple XIs all at once. And what's good is that in each attention head, we can process all of these n inputs or n words all at once or n tokens all at once. And so the way we do it is we generate this matrix that is basically each token stacked on top of each other on the rows, along the rows. And this, basically, this big X here represents all the tokens, attached, stacked up on one another, which basically represent a sentence, right? You can think of it as a sentence or a single sequence, right? Do you want to learn? So therefore, your query and key and value vectors could also now be stacked on top of one another to form query matrix, the key matrix, and the value matrix, right? How does the rest of the attention process looks like? So you do the dot product between each row, right? Between each row of the key and the query, and you apply the softmax operation along each row, and you apply the normalization to the entire matrix, and that will give you the A matrix. In shorthand, they represent it as this, like softmax of the key and or query and key matrices, dot products, etc., etc. And the attention output or the attention matrix is basically Z um, is another dot product between the A and the value matrix, right? And so this output will have the same dimension as your input. So it will have n rows for n tokens or n words in a sentence, and it would have the dimension of D, so D columns. So D represents your embedding space dimensions, right? Great. Now we can even parallelize this even further, which means that we can have multiple sentences all at once, right? So you can have your X as normal. Sorry, my bad, my bad. You can have the same sentence, but you can have multiple query and key and value matrices on it, right? So you may ask, what's the advantage of having multiple attention heads or multiple Q metrics or multiple key matrices? And it's because every attention head can learn independently of the others, can learn its own thing. So for example, one of the query matrices learns the grammatical role of the tokens inside the sentence, whereas the other one learns the, like the meaning of the word in the sentence, right? Or like relationship of the meaning of the words within one another, whereas the other one learns the grammatical relationships of the words in a sentence. And so you can have like multiple of these attention heads or like attention matrices going on in parallel. And what you want to do is that you want to reduce the dimensionality back to your dimensionality of your sentence or your, n tokens. So what you do is that you would concatenate all of these attentions that you've learned, and you apply one last dot product to them with this W naught matrix to kind of like fix the dimensionality. And you can also like you obviously learn this W matrix down the line as well. And so this allows you the output of the multi-hit attention for the same, sentence to be of the same dimension of the sentence, if that makes sense. Yeah. Okay, so that was it. So that was really like, attention, and that was like a big part of it. I'd be very happy to ask questions, like answer questions down the line if anything is confusing, and we can like walk through it slowly. Okay, so now that we know what embeddings are, how does the attention mechanism works, and how can we parallelize all of this information through attention heads, now we can talk about the transformer, like the architecture of the transformer. The transformer itself has two components. It has the encoder block, and then it also has the decoder block. So it's two separate things. I'm gonna now talk about the decoder block because the encoder block has like all of the steps 1, 2, 3 so far. So it's kind of it would be repetitive to talk about the encoder. What I want you to focus on the decoder block is to look at this like multi-attention head, and the input to this multi-attention head comes from the encoder. So the encoder has learned a lot of like self-attention or like relationship amongst the data, and it passes all of those features to the decoder block. The decoder also um, extracts its own feature and puts the features that the decoder has extracted alongside the information or the features that the encoder has extracted, and then it will continue the attention process forward, right? Now, the tricky thing about the decoder is that the decoder has learned to pay attention to the causal relationship in the data. How is that? Is that the way they do in a sequence is that they would mask the last token of the sequence, and they would allow the um, decoder to learn all of the information that comes prior to this masked token, right? So the decoder doesn't really pay attention to the last token because its job is actually to predict the last token. So it shouldn't see the last token, right? So we mask the last token, but the decoder learns information on all of the previous relationships, like the relationships between the previous tokens in the data, right? And down the line, it's supposed to output the last token, and if it outputted the last token wrong or right, then we generate a gradient based on the loss function, and we update all of the learnable parameters in the entire pipeline, right? Now, large language models could be both encoder decoder, and that's usually used for translations, but they could also be encoder only or decoder only. For example, Llama 4, which is you know a large language model from Meta or like Facebook. It is a decoder only architecture, and it has 2 trillion parameters. So just for reference, a human brain has about 100 billion parameters, and these networks have up to 2 trillion parameters, right? So now you can stack up all of this, decoder blocks or encoder blocks. You can stack them up into like layers, and you can keep like learning relationships within the data, and that would increase your the number of parameters in your model, but also it's shown to improve the capabilities of these models, as I mentioned. Okay, so are we there? We're good? Any questions? So this was basically, up to the end of the anatomy of transformer. And now now we can move on to the vision transformer. So how does this, architecture that was originally developed for translation of text, how could we apply that to images? The way you go is that you get your image, you break it up into patches. So now you have like multiple patches. Then you apply positional encoding on those patches, and there you go. Now you can treat each patch as an input that you can generate tokens based on, put it in an embedding space, and give it like a positional embedding for each patch of the image. And everything else is the same, which is very interesting because it's the same architecture that deals with images and not text very easily. Okay, so this allowed Meta to create basically like Dino V2. So Dino is a vision transformer that is able to perform really, really, really well on like natural images, right? And basically label that, oh, this is an image of a bear, this is an image of a fork, this is the image of the Buckingham Palace. So Dino does that extremely, really well. It's like simple labeling. But a very interesting property of the transformers is that you could visualize what the model is paying attention to. So for example, here you don't only have a fork, you have a fork and you have a doll, like a rabbit doll behind a fork. But with transformers, we can visualize the attention matrix and see that, okay, the model has learned to associate the word um, toothbrush. Sorry, I've been saying fork all the time. Sorry, this is a toothbrush. It has been learning to associate the word toothbrush with the shape, like with the pixels inside a toothbrush, right? And it's learned to kind of like ignore the rabbit in the background, right? So vision transformers are very easily explainable because we can also see what the model is paying attention to. I see something, yeah. Okay, so Eugene had a comment there. And so this is really nice because now these neural networks are explainable. You could do more than just like labeling images now. You could also do segmentation. So you have a picture of a rooster here, and then like the crown of the rooster could be segmented. So Meta developed this model called Segment Anything, and the Segment Anything again was trained on natural images, and any points that you click on, it will segment all of the components of that point. So if I click on the crown of the chicken, it will segment the crown of the chicken really, really well, right? And this serves as a very good like foundational model down the line. So with this vision transformers, not only you can label, you could also do segmentation, and you can see what the model is paying attention to by opening up these attention heat maps. Great. So Eugene mentioned self-supervision down the line. The reality of the world is that we cannot manually contour all of the images, all of the segments of an image, or we cannot have a label for each we cannot have a labeling word for each image that is out there on the internet. What we want the models to do is that we want the models to learn features of items that are unique in the physical world, right? So we want the model to know that this shape is a unique shape. Now, we as humans decide to call this a flamingo. It's irrelevant, right? Like we can learn that later on. But we want to know that if the model sees this shape, it's the shape of a unique item in the physical world that down the line corresponds to flamingo, right? So we want the models to be able to identify unique objects in the physical world. And to do that, you don't need to, manually label your ground truth data. You can just like have a lot of pictures of the physical world, and then you can like, if you're clever, you can teach them other features of those physical objects. And so the way they do it, the way they teach these features to the models is, for example, is through self-supervised learning. Like one very popular technique of self-supervised learning is the masked autoencoder, where you have this image and you mask part of it and you ask the model to kind of fill in the blanks, right, to draw what is missing. And so by doing this practice of drawing what is missing inside this masked input, the model learns how this unique item that is a flamingo looks like, or how should it look like in real life, right? Another technique for self-supervision was with Dino V. So again, you can click on the link and go to see the paper. So Dino was developed by Facebook again. And here in this process, you can teach the model a sense of kind of like zoomed in and zoomed out information. So you have two neural networks going on. One of them is a student, the other one is a teacher. The teacher is looking at the image as a whole, like a zoomed out part of the image, and the student is given a zoomed in part of the image. And so the teacher and the student, or like basically the student can learn from the teacher, where does this tiny information that they have fit in the bigger picture, to quote unquote, right? So you have like features at like a very local resolution, and you have features at a very high resolution, and you can kind of like have one network to kind of like learn both of the features all at the same time, going down the line. So these are like the self-supervision techniques that are used to train images without having to generate ground truth labels. And it really is important to kind of pre-train the model using the self-supervision, and then down the line train or fine-tune the model on your label data that is very limited and very small. So with that, we've reached Um, the conclusion slide. We see that the strength of the transformer is that they have positional awareness. They capture local and global relationships. Sometimes you need to be smart about it and do self-supervision and use that student-teacher architecture to kind of achieve a very good global and local relationships in your data for images. Sometimes you don't need to. It's all good. You'll figure it out. But a very important part of the transformer is that it's highly parallelizable. So you could process each token or each word or each patch in parallel to the other patches, and you can also process multiple images all at once or multiple sentences all at once. And all of the computation is running in parallel, which is fantastic. Now, you may ask, what's the catch? What's the weakness of the transformer? Is that they're extremely, extremely data efficient. So, for example, that segment anything model that I presented early on, that was trained on 1 billion images, right? Just like 1 billion with a big B, right? Like 10 to the power of 9 images of the internet that were unique, that were curated. And so the transformer is a very data hungry architecture. Another limitation of the transformer, at least for the text generation, is that it hallucinates, right? Like sometimes it just like generates words that are really not relevant to that context, right? They understand the context in some sort of way, but they may not necessarily output tokens that are relevant to the context that you have in mind, right? So humans are not really good at specifying the context within which they're talking about, right? And there's a lot of context that we assume that we understand when we talk to one another, but the computer doesn't see all that external context that is out there. So they may end up hallucinating because they don't have access to that extra information that is out there that we know, but they don't know, right? When we ask them. For this reason, they fall short on like local reasoning as well. So, if you ask how many R's in the word strawberry, they say like 2 R's, but strawberry has like 3 R's. Or if you ask them to do math, like 2 times 2 is equal 4. I mean, that's pretty easy, right? You can put it in a calculator, but they haven't learned the calculator. The transformers lack on like these like logical mathematical reasoning. And then the last thing is that they're extremely high. It takes a lot of energy to train these transformers. As I mentioned, you have like 10,000 GPUs going all at once, and these GPUs, each of them consume about 250 watts, up to, like 500 watts or like 700 watts. And so if you have 10,000 of these in parallel, they consume a lot of energy. One thing that, Elon Musk has done to train Grok is that they basically connected basically a natural gas processing mine, so like a natural gas pipeline directly goes to XAI, and it's like they burned all that gas to generate the electricity to train these transformers, and it's very depressing for the climate, obviously. But if you have clean energy, if you have nuclear energy, it's like very easy to train, like it's easier to supply this amount of energy. Anyways, so that was the uh, transformers. In conclusion, they're like very versatile, but they have some weaknesses as well. So now I'm going to take a look at the chat. So does vision transformer have been applied to image segmentation using heat maps? Or is it more applied to image classification? So yeah, Matthew, like they've been applied to image segmentation. As I mentioned earlier, we have the segment anything model or SAM. And yes, there is medical adapters for SAM. I'm sure Eugene is already mentioning it. But yeah, so there's already medical SAM adapters that gets the regular SAM and fine tunes it on medical images because medical images don't really look like the natural images out there. So thank you, Eugene, for like applying the links to all that stuff. And that was the Transformers. So
Thank you,
let's
Hossein.
see. Do you guys have any questions?
Yeah, just to add to that regarding whether vision transformers can sort of do segmentation as well. I supplied a couple of links of two of the probably most famous models out there. If you've ever done any like high challenges with the brain tumor segmentation challenge, these models are used quite pretty often. People use NUnit probably the most often, and then there's TransUnit, SwineUnit, or UNet, which is trying to combine units and convolutional unit network blocks and transformers at the same time to get the best of both worlds. Something that I've also been personally wondering about that the whole whether you can use transformer to do vision transformer to do segmentation as well, the heat maps because you have multiple attention heads, and then so the different multiple attention heads is pay attention to a different thing of the original image. So sometimes one of those or some of those attention heads could be visualizing a different part of the segmentation as well. You just have to sort of turn that into a segmentation mask of what you're doing. So something that's Jose, if you like open the first link that I give, I'll just give a quick spiel on this. It is something that my colleague Juan and I have experimented with quite a lot. I mean, not
This
this one,
one?
the
Oh,
hipped one,
this one. The
but just as an example, this is a scaling vision transformer to gigapixel histopathology images, but obviously doesn't limit yourself to just histopathology images. But a thing about histopathology images is that extremely large and there's multiple different resolution scales. And so this is where you can take advantage of the fact that the transformers can take into account of the context of the images. So you can do this at multiple different levels of resolutions for the original digital pathology images like this is doing here. So you can extract information on the patch level and on the region level and on the whole slide level. And what I wanted to illustrate with the heat maps is if you go down a little bit, yeah, this
Here?
paper was first, I think came out in 23 or 22, but it was one of, wait, is this a heat map or is this like a different type of, I'm not
Yeah,
sure if I
it
can
is.
see that. Okay, maybe it's just your screen. But anyway, this is a
Wait, wait,
heat.
what do you see? What do you see? Wait a minute.
I see a little bit lighter, like on my screen, but I don't know if others. But if you
Oh,
like
interesting.
if you look at the paper itself, this is a heat map that you can obtain from the vision transformer of the two. Let's say you don't even care about the two levels of the vision transformers, but you can do this kind of heat map visualization of the vision transform from the vision transformer of the original input image. Because of different attention heads, you're sort of visualizing. You ended up sort of visualizing a different type of classification of your cells. So on the first row, you're visualizing the tumor stroma, and on the second on the second row, you're visualizing like the white space, and there's a few other plots that if you almost like another way to classify different cells for your input images, but it could be used for other applications too. Yeah, so that's what I
One thing
wanted
that I
to.
wanted to, yeah, thank you, Eugene. That was really good. Another thing that I just wanted to add is that all it is like vision transformers that can perform segmentation. Uh, some of them, the good ones, like are available in the MONAI platform.
Hmm.
So MONAI is a medical image processing framework or like package that was developed by NVIDIA. And here you have like access to all of this pre-trained models. Either they're like in the units, so either they're units or GANs or transformer-based models, and you can use them directly and you can like fine tune them instead of training things from scratch, which is kind of nice. So definitely make advantage of the Monet platform, and they have a lot of other functionalities, so like for like evaluation, like different loss functions, different evaluation metrics, different visualization techniques. It's all like implemented in Monet, so it's super useful.
Yeah,
Okay.
yeah. Do you guys have any other questions? Matsuba, any other questions? I'm just gonna call on you now because I know you have questions. All right.
Yeah. Well, if not, then yeah, we
Cool.
can wrap up
Thank
the
you.
session. This will be uploaded. Yeah.
Great. Awesome. Perfect. Yeah, absolutely. The vanilla, I would like you don't have to. We don't have to go to the vision transformers and whatnot for the applications. It's just sometimes it works better for different applications. But I feel like from the most of the applications that you see, it's a vanilla. You would call it a good old unit or a vanilla unit with your original samples with your local data that would work well enough, honestly. Especially if you do pre-train and fine tune from a large data set. Um, Great. Thank you so much. And we will proceed another day. And what day is that? Yeah,
I
that's
think
going to
it's
be
Wednesday.
Wednesday. Yeah. So
Yeah. Yeah.
Juan Duran is going to go through some practical exercises from the stuff that we learned from today. And then on Thursday, Hossein and I are going to host another practical sessions on some of the more advanced vision language models as well. Great. Thank you very much. See you next time. Bye.
Bye.